Hey y'all, so this is your lecture on implicit differentiation. So if you'll remember, section 3.4 was a part of unit 3. It was the last section in unit 3, but because of time, I chose to pull it out of unit 3. So it's now just a lecture video assignment. So your job is simply to watch this lecture video and then complete the corresponding implicit differentiation assignment in ALEX, but you won't be tested on this material in any way, in like a quiz or a test or anything else. The only thing you'll do is complete that homework assignment and watch this lecture video. So let's see how quickly we can get through it. Now, implicit differentiation is much different than regular differentiation. Basically, taking derivatives implicitly is much different than taking derivatives explicitly, which is what we've been doing the whole time. Mostly because instead of just dealing with one variable, usually x, we're going to be dealing with two, x and y. So let's see if I can explain this well for you. So let me go ahead and get a pen. All right, and this little tablet that I have in my office is a little more difficult to work with than the ones in the classrooms, but this is what we need to use for today, so we'll see if we can make it work. So every function for which we have found the derivative thus far in the course has been explicit. So it's a lot harder to write on this tablet, so give me some grace on the handwriting. So every function for which we have found the derivative thus far in the course has been explicit, meaning that the y was isolated. So for example, we found derivatives of functions like y equals 3x plus 2 or 3x minus 2, or y equals x squared plus x plus 6, or y equals negative x cubed plus 2. You could find the derivative of all of those, right? This one would be dy dx equals 3. Okay, this one, so that's this one right here. All right, this one, on the other hand, would be dy dx equals 2x plus 1. Right? And then this one would be dy dx equals negative 3x squared. That's taking the derivative explicitly. That's what we've been doing the whole semester. But when it comes to more complicated functions or equations, like this one we see right here, y to the fifth plus 8y cubed plus 6y squared x squared plus 2yx cubed plus 6 equals 0, well, we can't isolate the variable y. There's not a way to solve for y. So because there's not really a way to solve for y, we can't take the derivative explicitly. We have to use the process of implicit differentiation, or taking the derivative implicitly. So that's what we're going to learn how to do in this lesson. So your blank here, let me go back to my black pen here. Therefore, we must use implicit differentiation. Thankfully, we only have a few blanks on this one, so hopefully the handwriting won't get too bad, but this tablet is rough. Okay, so I will show you how to do this in the following examples. So this is what your directions are going to say when you get to your ALEX problems. For the curve defined by the equation below, so we're looking at 7y squared plus 4x squared equals 5. Find dy dx. Write your answer in terms of x and y. Do not try to write your answer in terms of a single variable. Okay, so what we're going to do is look at this as three different terms. Let me get my highlighter. This is what I want. Okay, so we have this term, and do a different one, this term, right? So we're going to take the derivative of each one. Now what we're going to do is, if we have a y to deal with, okay, like 7y squared, we're still going to take the derivative, but we're going to write dy dx next to it. Okay, so for example, the derivative of 7y squared would be 14y, right? But we're going to write dy dx next to that. Now, if we're taking the derivative of something with just an x, like 4x squared, then we can just take the derivative normally. We don't need to put dy dx next to it. So here's the plus sign that I'm carrying down. And I'm going to write 8x because the derivative of 4x squared is 8x. And then that's equal to the derivative of any constant is 0. So we'll just put 0. Okay, so we look at each term individually and take its derivative. If we are taking the derivative of the variable y, we're going to still take the derivative. 7y squared, the derivative is 14y. But we're going to just put dy dx next to it. If we're taking the derivative with x, we just take the derivative normally. The derivative of 4x squared is 8x, no problem. And then the derivative of any constant, of course, is 0. So we now have this. And once you get to this point, what you want to do is isolate dy dx. Essentially, you're looking at this as an equation in which you want to solve for dy dx. Okay, so the first thing I'm going to do is bring my screen down just a little bit. It's easier to write when it's higher. Okay, the first thing I'm going to do is take this 8x here and move it over to the other side with subtraction. Okay, so this will become 14y. Oh, must have clicked something. Let me click off of that. There we go. 14y dy dx equals negative 8x. Okay, now I'm trying to solve for dy dx, so what I'm going to do is divide both sides by 14y. So I'll divide this side by 14y, and I'll divide this side also by 14y. So obviously that cancels over here. And we've done what we wanted to do, which was isolate the dy dx. So we have dy dx equals negative 8x over 14y. And so we can simplify that just a little bit. If we wanted to, we can leave it like that. I tried it in Alex, it takes it like that. But 8 over 14 would reduce to 4 over 7. So you could write it as dy dx equals negative 4x over 7y. Okay, and this would be the part that you would type into Alex, the negative 4x over 7y. So you can see implicit differentiation is a lot more difficult than explicit differentiation, but let's do some more examples to make sure we're good. So let's look at the next one. This one looks a little more complicated because we have something with an x in it and with a y in it. Okay, so still 3 terms though. Let me get that highlighter ready. Okay, so here's that. Oh, it did not change to a highlighter. There we go. Let's try that. Okay, there's that first term, that second term, and then the third term. Okay, so I see the first term just has a y in it. So I'm going to go ahead and take the derivative. The derivative of 5y to the fourth would be 20y to the third. But next to it, I'm going to put a dy dx since I took the derivative with a y. So 20x to the third. And then next to it, I'll put dy dx. Okay, now let's talk about this one. Let me see if I can write that a little neater for you guys. You can get your paper ready while I'm doing this. I don't know that it's much better, but there we go. Okay, so now let's do this green one. Now this is interesting because when we were up here, I said, okay, if it's a y, you take the derivative and you write dy dx next to it. If it's an x, you just take the derivative. You don't have to write anything next to it. But this one has both an x and a y. So we're going to have to treat this one a little bit differently. Okay, what we're going to do here is we're actually going to take the derivative twice. So first, we're going to take the derivative with x being our variable. We're going to pretend y is just a constant. Then we're going to take our derivative with y being the variable and pretending x is the constant. Okay, so let's take the derivative with y being the variable first. So if y is the variable, then the derivative is just what's in front of it, 4x. Okay, so here's the first time we're taking it. I'll do this time in green. Let's see. There we go. So we're going to say plus 4x. But since we took the derivative with the variable y, we're going to put dy dx next to it. Now we're going to take the derivative a second time, but this time we're going to let x be our variable. So we won't need to write dy dx. If x is our variable, then we're just left with the two constants on the outside of x, which are 4y. So then we would just do 4y. And of course, the derivative of any constant is 0. So what we would say here is that we look at this middle term and we take the derivative once with respect to x, meaning treating x like our variable. And then we take the derivative a second time with respect to y, meaning treating y as our variable. So when I treated y as my variable, the derivative was 4x. And since I treated y as my variable, I put a dy dx next to it. When I treated x as my variable, the derivative was 4y. And since I was treating x as my variable, I did not need a dy dx next to it. And then, of course, the derivative of any constant is 0. Okay, so now I have 3 terms, right? We've got, I'm going to underline them, 1, 2, 3, really 4 if you count the 0 too. But I have 3 terms that are to the left of the equal sign. And of those 3 terms, 2 of them contain a dy dx. So now to get my final answer, my job is to isolate the dy dx. So if I have 3 terms on the left-hand side and 2 of those 3 terms have a dy dx in them, then I need to move over the term that does not have a dy dx. So 4y does not have a dy dx. So I'm going to move that over to the other side with subtraction. So let me move this down just a bit. So this is going to become 20x cubed dy dx plus 4x dy dx equals negative 4y. Okay, so I still have those 3 terms. 1, 2, 3. But now those 2 terms are by them with the dy dx are by themselves on the left-hand side. So what I can do now is factor out the dy dx. So my next line becomes dy dx times 20x cubed plus 4x equals negative 4y. Now remember, my goal is to solve for dy dx. So I've now factored dy dx out. So this is dy dx times 20x cubed plus 4x. So if I need to isolate the dy dx, then I just need to divide both sides by that expression in parentheses, which is 20x cubed plus 4x. So my final answer is going to be dy dx equals negative 4y over 20x cubed plus 4x. Okay, and this is the part, oops, this right here is the part that you would put into Alex. Okay, so you now have 2 good examples of implicit differentiation, but it's hard, so we're going to do 6. Okay, and feel free to pause the video at any time if you need to back it up, look at something again, pause it so you can write everything down. That's the nice part about a video lecture. But for now, let's take a look at this next one. Now be careful, because I want you to notice that they kind of try to trip you up on 4. Oh, that's 5. Okay, we'll get there in a minute. Sorry. I was going to show you they're asking for dx, dy, but we'll get there in a minute. Let's do one more dy, dx before we panic. So going to number 3, we have for the curve defined by the equation below, find dy, dx. Write your answer in terms of x and y. Do not try to write your answer in terms of a single variable. So as you go through this homework, you're going to notice that the directions are always the same, except for one thing. Sometimes they'll ask for dy, dx. Sometimes they'll ask for dx, dy. But don't panic. It's not that hard. I'm going to show you when we get to example 4. But for now, let's do example 3, which is another dy, dx example like we did in 1 and 2. So it looks like we have negative 20x squared y squared equals negative 3. So I'm going to get my highlighter because I notice I have 2 terms. So here's my first term and here's my second term. Now my second term, the one in green, no big deal. It's a constant. It's going to zero out. But I notice here that I have a negative 20x squared y squared. So I'm going to have to do the same thing that I did here, where I take the derivative twice. Once treating x as the variable and once treating y as the variable. So let's try to do that. There we go. Make sure I get it back on the right problem. Okay, so let's treat y as the variable first, just to get it over with. So if y is the variable, then I'm going to bring this power of 2 down. Okay, so if I bring the 2 down, and then I'm going to also multiply it by everything that's stuck on the front. So 2 times negative 20x squared, and then that would be y. Okay, so I have 2 times negative 20x squared and then a y. And so since I was treating y as the variable here, I'm going to have to write dy dx next to it. Okay, then I'll have to do an addition symbol. And now I'm going to do the same thing, but I'm going to treat x like my variable. So I'm going to take the power on x and bring it to the front. So it also happened to be a 2. And then I have to write everything else that was there down because I assume those are coefficients. So negative 20 and then y squared, because those are coefficients on the x. And then we have the x. Now remember, when we treat x as our variable, we don't have to write the dy dx. And then that's equal to 0. So that's looking pretty complicated right now. So let's see if we can simplify this a bit. Okay, so we have 2 times negative 20. So this one would become negative 40 x squared y dy dx, and then plus negative 40 y squared x, or you could write it as xy squared. That's the same thing, equals 0. Now that's plus negative 40. So quite honestly, we should probably just take this and write it as a negative, right? Okay, so that's something I can deal with a little bit better. And let me use a highlighter because I think that might be a little easier to see than underlining it like I did in the last problem. So now we have this term, that's one term, right? And we also have this term. And we're supposed to be solving for dy dx. So I have 2 terms on the left. One has dy dx, the other one does not. So I'm going to take the one that does not have dy dx and I move it over to the other side with addition. So then this becomes negative 40 x squared y dy dx equals 40 y squared x. Okay, and now my job, remember, is to solve for dy dx right here. So I just need to divide both sides by this stuff right here. So this is going to become dy dx equals 40 y squared x, that's this thing over here, divided by this thing over here, negative 40 x squared y. So that's actually my answer. That's my dy dx. I just need to simplify it algebraically a little bit. So obviously the 40s cancel, but I do still have that negative. So I'll put the negative out to the front. Okay. And then I have 2 y's in the top and 1 y in the bottom. So one of the y's in the top cancels with the y in the bottom. And I have 2 x's in the bottom and 1 x on the top. So one of the x's in the bottom cancels with the x on the top. Wow, so that simplified a lot. Simplifies all the way down to negative y over x. So it looks like dy dx is equal to negative y over x. And this right here, of course, is the part that you would type into Alex. Okay, so I hope you're kind of starting to get it, but it's like, I'm sure it always feels like you're kind of starting to get it, and then I throw you a curveball, which is what it's going to feel like a little bit here. You can see, remember we talked about they were asking for dy dx, and now they're asking for dx dy. Here's the thing. You're going to work it the same way, and you're actually going to find dy dx. Then you're just going to flip your answer. You're going to take the reciprocal of your answer to make it dx dy. It is not going to be harder than what we've been doing, I promise. So let's take a look at this one and see what we can do. Okay, so this is your number 4. So we only have 4, 5, and 6. You're on the home stretch. We've done the first 3 already. So it says, for the curve defined by the equation below, write dx dy. But we're not going to do that. We're going to find dy dx and then flip our answer. Trust me. So I'm looking at this, and I'm going to highlight my different terms just because I think that's easier. So 1, 2, 3, 4. So I have to take the derivative of each one. So I'm going to go back through the rules that we've been talking about. Okay, so I know that if it just has a y, I'm going to take the derivative normally and then just write dy dx next to it. Okay, so 7 times 4 is 28. So the derivative of 4y squared would be 28y to the 6th. But because I took the derivative with respect to y, or treating y as my variable, I'm going to write dy dx next to it. That didn't come out very nice, so I'm going to try again. Dy dx. Okay, now this one's the tricky one. I see an x and a y, so I know, just like last time, I'm going to have to take the derivative twice. Once, acting as if y is my variable. Second, acting as if x is my variable. So I'll go ahead and do the y as my variable one first. I'll do this one in red. So if y is my variable, then I treat x like it's a constant number. So I'm going to bring down the 9, keep the x there like it's a constant number, and then it would be y to the 8th when I reduce that power by 1. Okay, but since that still didn't come out very good. That's okay. You know that's an 8. But since I treated y as my variable, I have to write dy dx. Okay, now I need to do it again. Now, I'm going to write another subtraction symbol because it had a minus in front of it, okay? So I'm doing it again, this time treating x as my variable. Well, if x is my variable, then there's no power to bring down. Y to the 9th is just the coefficient. So it's just y to the 9th. Okay, but that time I treated x as my variable, so no need to write dy dx. Okay, then I'll do plus, and this one has x, so great, can take the derivative normally, no dy dx. So the derivative of 3x squared is 6x, and then an equal sign, and the derivative of 6 is 0. Okay, so now I really got to take a look at this, see how many terms I have. So it looks like I have 1, 2. Remember, terms are separated by addition or subtraction. 3, 4, and then of course my 0 over here. But of the 4 terms over here, 2 of them have a dy dx in them. So I need to isolate those. I'm going to add the y to the 9th over here and subtract the 6x over here. Okay, so we have 28y to the 6th dy dx minus 9xy to the 8th dy dx equals. Now I've added over the y to the 9th, so I'm going to put y to the 9th and subtract it over the 6x, so minus 6x. So now my two terms that contain a dy dx are on the same side, right here and right here. And so just like I've done every other time, I'm now going to factor out that dy dx. So I end up with dy dx times 28y to the 6th minus 9xy to the 8th is equal to y to the 9th minus 6x. And so you know the drill now. I can solve for dy dx by just dividing by everything in these parentheses. So dy dx is equal to y to the 9th minus 6x over 28y to the 6th minus 9xy to the 8th. Now, if I were asked to look for dx dy, if I were asked to look for dy dx, that would be my answer. Y to the 9th minus 6x over 28y to the 6th minus 9xy to the 8th. However, I was asked for dx dy. So all you have to do is flip it. Okay, so dx dy is equal to 28y to the 6th minus 9xy to the 8th over y to the 9th minus 6x. All you have to do is flip it. Okay, so there's example 4. Only 2 left to go, and I'm going to try to make them as easy as possible. See what I can do for you. 6 is kind of a doozy, but we're going to do it together. So looks like we have another dx dy one. So again, we'll find dy dx just like we always have, and then just flip it at the end. Okay, so this looks complicated. Looks like we have x cubed times x squared plus y squared equals y squared. So you are allowed to move things around a bit if you want to. So one of the things that I'm going to do here is go ahead and distribute in this x cubed. Okay, so x cubed times x squared is x to the 5th. X cubed times y squared is x cubed y, there we go, x cubed y squared, and then that's equal to y squared. I'm going to do implicit differentiation on this function. That seems much easier and much more similar to the problems we've been doing so far. So I still have 1, 2, 3 terms here. So I see one of my terms has an x and a y, so I'm remembering that I'm going to have to take the derivative twice, once pretending, or not pretending, but assuming the variable is x, and once assuming the variable is y. And then I have just an x where I take the derivative normally, nothing else, and then just a y where I take the derivative normally, but then tack a dy dx onto the end. Okay, so let's take a look at this one. So the first one, I just take the derivative normally. So the derivative of x to the 5th is 5x to the 4th. No big deal. Now here's the one where I have to take it twice. Okay, so the first time I'm going to pretend y is the variable. So if y is the variable, I'm going to bring the 2 down to the front. Okay, and then x cubed is just a coefficient. So I'll just write it down, x cubed, and then y. Okay, but since I was letting y be the variable, I have to put a little dx dy on it. So I'll do a plus sign because it was plus in front. And now I'm treating x like the variable. So if x is the variable, I bring the 3 down. Also, y squared is just a constant, so y squared. And then the x becomes squared. But since I was treating x as the variable, no reason to put dy dx. And then we have equals, and then 2y, the derivative, I'm sorry, y squared, the derivative would be 2y. But since we let y be the variable there, of course, we put a little dy dx. Okay, so taking a good look at this, I see that we have 1, 2, 3, 4 terms. Okay, so of those 4 terms, 2 of them have a dy dx in them. So I need to get that dy dx on the same side. I think what I'm going to do is take this 2x cubed y dy dx and move it over here, because that would probably just be the easiest thing. So I'm going to go back to my pen. And if I subtract this middle term over here, this becomes 5x to the 4th plus 3y squared x squared is equal to, and then we have the term that was already over here, 2y dy dx minus 2x cubed y dy dx. Okay, so I still have my 4 terms. You can see them here. But now of those 4 terms, the 2 that contain dy dx are all on the same side. Okay, so I'll proceed like I normally do, which is factoring out the dy dx. Okay, so we have 5x to the 4th plus 3y squared x squared is equal to dy dx times 2y minus 2x cubed y. There we go. Okay, so I want to isolate dy dx. So I'll divide both sides by this whole set of parentheses that is currently being multiplied by dy dx. So we get 5x to the 4th plus 3y squared x squared divided by 2y minus 2x cubed y equals dy dx. But remember, I was asked for dx dy, so I need to flip it. Okay, so this tells me that dx dy is equal to 2y minus 2x cubed y over 5x to the 4th plus 3y squared x squared. And there you have it. So again, anytime you need to, pause the video to write something down or take a break or whatever, you absolutely can. Just making sure that I have the same thing in my notebook. Okay, good. I actually worked it differently in my notebook, so it was like tripping me up because it looked a little different, but it's equivalent. So anyway, there you have it. There's number 5. So we only have one more left. This is kind of the one that's a doozy, but I know you could do it. So let's take a look at this last one. And of course, you guys can always come and ask questions on these if you have any questions. Okay, here's the last one. All right, so this one's a little tough. We have, where'd you go? All the way up at the top. There it is. So we're back to dy dx, thankfully. So we won't have to flip it at the end. But we have the square root of xy equals 8x to the 4th, y to the 7th. Okay, so here's how I would do this. I think I would first rewrite it. So instead of square root of xy, I think I would write that as the square root of x times the square root of y, or even just square root of x, square root of y. Maybe that's easier to see. Okay, so square root of x, square root of y. Now on this right-hand side, I would at least distribute the 8 in. So 8x to the 4th plus 8y to the 7th. Then I think I would rewrite it even once more because I want to be able to use the power rule when I'm taking these derivatives. So I'm going to write this as x to the 1/2, y to the 1/2 is equal to 8x to the 4th plus 8y to the 7th. So I'm going to start the process of implicit differentiation. So I have 1, 2, 3 different terms. Now these two terms over here on the right, those are going to be easy because the one that has an x in it, just take the derivative like normal. The one that has a y, take the derivative like normal and then shove a dy dx on it. Not a big deal. It's going to be this one. I see this term. Remember, a term is a string of factors multiplied together, separated by addition or subtraction. So that is a term because those two are multiplied together. And so since I have both x and y in the term, I'm going to have to take the derivative twice. Once letting x be the variable and y be the coefficient, and one letting y be the variable and x be the coefficient. So let's do that one first because it's harder. We'll go ahead and get it out of the way. And it's on the left anyway, so that's kind of convenient. So let's let y be the variable first. Okay, so if y is the variable first, I will take the 1/2 power and bring it down to the front. So 1/2, okay. And then this is just a coefficient, so 1/2 x to the 1/2. All right, and then I have to do 1/2 minus 1 for the power because I brought it down. So 1/2 minus 1 is y to the negative 1/2. Okay. All right. Then I have to put an addition sign and I got to do it again. So this time I'm going to let x be the variable. Oop, almost forgot something. Hold on. Since we let y be the variable in that one, we need to put a dy dx next to it. Okay, perfect. Now we need our plus sign. Now we're letting x be the variable. So we won't need dy dx this time, but the process is similar. So if x is my variable, I bring down that 1/2, okay? And then I let y to the 1/2 just be a coefficient, constant number. And then I have x, and then this 1/2 minus 1 is also negative 1/2. Okay, so that was kind of tough, but these will be easy. The 8x to the 4th, the derivative is 32x to the 3rd. Okay, and 8y to the 7th, the derivative is 56y to the 6th. But we will need a dy dx next to it. Okay, so I'm looking to see if it'll let me keep these in the 1/2 format, and I think it will. I don't think it's going to give me a problem. Okay, so I'm looking at this now, and let's see how many terms I have. So here's the first one. There's a term. Here's the second one, third one, and fourth one. Okay. So I'm going to put the two that have dy dx in them on the same side. So I'm going to take this 56y squared, or I'm sorry, 56y to the 6th dy dx. I'm going to bring it over here by subtracting it. Okay. And I'm going to take this 1/2 y to the 1/2 x to the negative 1/2 that does not have a dy dx, and I'm going to bring it over there by subtracting it. Okay, so that gives us 1/2 x to the 1/2 y to the negative 1/2 dy dx minus 56 y to the 6th dy dx equals 32x to the 3rd minus 1/2 y to the 1/2 x to the negative 1/2. Okay, still 4 terms, just the dy dx's are now on the same side. So here's term 1, here's term 2, here's term 3, and here's term 4. Okay, so I'm going to factor out these dy dx's right here. So that gives me dy dx times 1/2 x to the 1/2 y to the negative 1/2 minus 56y to the 6th is equal to 32x cubed minus 1/2 y to the 1/2 x to the negative 1/2. And then you know the drill by now. Once we get dy dx by itself, you're just dividing both sides by whatever's in these parentheses. Okay, and so we get dy dx is equal to 32x cubed minus 1/2 y to the 1/2 x to the negative 1/2 over 1/2 x to the 1/2 y to the negative 1/2 minus 56y to the 6th. Oh. Let's see. There we go. Okay, and this would be what I would put in. There's a couple different ways you can rewrite it, but it takes it like that, so that's fine. Okay, I wrote down notes about how it would take it, so that's what I'm checking right now. Yeah, it'll take it like that. Okay. All right, so that's the whole thing. Not the easiest thing in the world, but you have 6 good examples, and I think there's only like 8 in the homework. So make sure that you watch this lecture video, take really good notes, and then go do that Alex assignment and let me know if you have any questions. But again, I won't put this on the test or the final exam or any quizzes or anything like that. All right, let me know if you have any questions.